Hey, welcome to Analog Output. This is Noise Bells. This is a module I designed based on some ideas presented by Elliot Williams in an article from 2015 in Hackaday called Logic Noise, More CMOS Cowbell. This is part of a series of articles about using logic chips to make music. And let's take a look at it. Here's the circuit board, and you can see there isn't much there. There's 3 chips and a few discrete components. There's pots and switches on the other side, 4 jacks. This first chip is a Schmitt trigger inverter IC. There's 6 inverters on the chip, and you can make a very simple relaxation oscillator with one of these inverters just by adding a capacitor and a resistor. So one section of this module uses 2 of these inverters to make 2 simple square wave oscillators, and the resistors are these 2 pots here, so you can tune the frequencies of these 2 oscillators. And then the outputs of these 2 oscillators go into this chip here, which is an exclusive OR IC. It's got 4 XOR gates on it, and the 2 oscillators go into one of these gates, and if the 2 frequencies are not something simply related to each other, then the frequency structure you get when you do the XOR turns out to be something very complicated. You get lots of sums and differences of multiples of the 2 frequencies, and that kind of complicated structure it's characteristic of bells and other percussion instruments. But to get a percussion sound, you need a loudness contour that turns on very suddenly and then decays away more slowly. So here are some resistors and capacitors and diodes that form a simple envelope generator. One with a very fast attack and a slower decay, which you can control with that pot. And this envelope is used to control a voltage controlled amplifier. Now, normally you think of a VCA as some rather complicated circuit, but here we have a VCA that consists of a quarter of this IC and 1 resistor, which sounds crazy, but it is true. So the IC is an analog switch chip. It contains 4 analog switch units, and these are kind of like doorbells. So in a doorbell you have 2 wires that are normally not connected to each other, but when you push the button it connects them. And similarly in this chip you have 2 pins that are normally disconnected, but when you push the button it connects them. Only it's not literally a button, it's a control pin. So when you send an off signal to the control pin, the input and output are disconnected, and when you send an on signal to the control pin, they're connected. So what you can do is this. You can take the control voltage, let's say for instance it's 3 volts, and attach it to the analog switch input, and take the output of the XOR and attach it to the control pin. Now the XOR output is binary, which means it's always either off or on, and when it's on, the switch input and output are connected, so you've got 3 volts on the output pin. And when the XOR output is off, the input and output are disconnected. Now that doesn't mean the output is at 0 volts, it means it's floating. It doesn't have a well-defined voltage, which is not what we want. So we connect a resistor between the output pin and ground. So now when the input and output are connected, the output's at 3 volts. But when they're disconnected, the output's still connected to ground through the pull-down resistor, so it's at 0 volts. It's well-defined 0 volts. And that means now the switch output looks just like the XOR output, except instead of going from 0 volts to 12 volts, it goes from 0 volts to 3 volts, or 0 volts to 4 volts, or 0 volts to 1 volt, or whatever the control voltage is. And that's exactly the kind of behavior you want from a voltage-controlled amplifier. Now, it only works because the input signal is binary, so it can be used as a logic signal. It can turn on or off the analog switch. It wouldn't work for sine waves or triangle waves or ramp waves, but for pulse waves it works just fine. Now the Hackaday article actually had a different VCA consisting of 2 diodes and a resistor, which sounds even crazier, but it actually works more or less. But I think the analog switch VCA works better, so that's what I used. All right, so you apply the envelope as a control voltage and you get a sound like a bell. And the switch output goes to a transistor buffer and from there to the output jack. Now that's if this switch is down, and if the switch is in the up position, then the envelope generator and VCA are bypassed and it just sends the XOR output directly to the output jack. So you get a noisy drone sound. Now they called this a cowbell circuit in the article, and then they described another circuit which they called a hi-hat circuit, which was exactly the same except it used 6 oscillators instead of 2, combined using 4 XOR gates instead of 1. And the problem is if you build the cowbell circuit, then you don't have enough inverters and XOR gates left in these chips for the hi-hat circuit. So instead what I built was something sort of halfway between the cowbell and the hi-hat. It uses the remaining 4 oscillators from this chip combined using the remaining 3 XOR gates from that chip. And then the last XOR gate goes either through a VCA with an envelope generator or straight to the output. It's exactly the same as the cowbell circuit from that point on. And the sound isn't as complex as the hi-hat circuit, but I think it's complex enough to do some interesting things. Let's have a listen. So that's Noise Bells. It's simple, it's kind of weird, it's a little hard to control, it's got some interesting fun possibilities, I think, and I hope you enjoyed it. If you did, subscribe, and stay tuned. Got more coming up soon here on Analog Output, including the start of a new synthesizer. So Watch for that. See you next time.